All right, I think we're fine. Sorry for the fumble. I thought Windows was okay, but apparently it's not. All right, so I'm gonna present Julia Bugs. So this is the work by me and Hong, and Hong mentioned this in the morning. I will go into more detail at this point. And of course, you see Andrew Thomas. Andrew Thomas was one of the original developers for Bugs, and it's been a great inspiration and a source of knowledge. So this is what I want to convey right today. So Julia Bugs implemented Bugs, and we made some extensions, including allowing external functions and that. And the Bugs language itself, it offers, I think, very user-friendly syntax. And it also provided quite a powerful way of thinking about modeling. Then Bugs, this is really, I think Sam in the morning I've talked about this trade-off between expressivity and amenability to analysis. I think Bugs is a great trade-off on that regard, and we're aimed to really deliver a high-performance inference engine at the end of the day. Just a bit on the Bugs language, right? So it is one of the first PPL. It might be the first widely used PPL. Again, it has a sustained popularity these days. People are still using it for education and also applied. It really describes a DAG, right? A probabilistic graphical model. It contains finite amount of nodes and edges. And what DAGs are great about is really you can easily get the dependency information out of it. I'll use a really simple model, try to demonstrate the syntax. Sorry, I think there's a bit of a smudge in between, but I think we'll manage. You can see the graphical model on the left, right? It's a really simple one. I use dashes for deterministic nodes, right? It's just some computation. And on the right is the model written in the original Bugs syntax. Right, it's actually pretty standard. The only thing this is kind of non-standard is the equal sign, which is the equal sign of R and S for the matter. The thing about this is from the graphical model to the program is really simple, right? You see the play notation, and you translate the play notation to a for loop, and that's pretty much it, right? Yeah. You can also use the Julia macro. I think we have demonstrated this Julia macro in the morning and maybe one of the later talks. You can see it's almost one-to-one, though the only thing, of course, we were using the proper equal sign now. Just a bit on the Bugs syntax. So I have the program and the data on the left. Right, and the one thing I want to bring your attention to is the missing. Right, you can write a missing in the data to indicate that it's unobserved. The thing about Bugs is that the order of statements doesn't really matter, because right now it's describing a graph, and it's describing this concrete thing, and the order is not a sequential execution model. Also, you don't need to give the size of arrays, right? This is determined by compilers. I am throwing some large words, partial evaluation here, but the fact is, a model in Bugs, right, is specified by both the program and the data, right? We need the data and the program both. And because indices can be expressions, this really means you need some sort of a partial evaluation to determine the dependency relationships, right? To determine which variable is associated with other variables. We also need to distinguish something called transformed variables, right? This is Stan have a standout block for this, but it's really just something that you can compute before the model evaluation, before the inference. And also we need to determine which variables are observed and unobserved, for that matter. I also want to say something about this graphical representation of the bugs. A bugs program always describe a DAG. And we check this in the compiler. It's a requirement. And also the graph, interestingly, can be seen as a trinity. I don't know. It can be seen as a directed probabilistic graphical model. It's also a dependency graph, right? And also at the end of the day, it's a computation graph. This computation graph idea, I think, being revived by TensorFlow, and it become a common language these days for computation. And this is really the source of our, we're going to build high performance because we have this graph structure. Talk about inference, right? Inference is important for statisticians. The Julia bugs. Again, Hong mentioned this interface that you can compute log density, you compute gradients of a probabilistic program. Julia bugs support that interface, and thus it just supports all the inference algorithms of Turing. Not all, sorry. It's some inference algorithms and more inference algorithms incoming. I should mention you support HMC and NUTS, which is not available to bugs user before. Now it does. We do have a Gibbs implementation, but the performance is not quite on par as what we hoped, because we really want to. So this is one of the motivations of starting this bugs project. We want a really high performance Gibbs algorithm, and we're working on it. Talk about future directions, right? So, like I said, high performance Gibbs is our one of the primal targets, and also there are a lot of really nice things we want to do, right? Talking about analysis and program transformation. I'm just listing two things here. The first one is conjugacy analysis, right? This is so essentially, there's a lot of existing knowledge in the statistics and the probabilistic modeling community, and we do want to transfer some of them into the probabilistic programming language analysis space. And again, the second point on the list there is automatic marginalization is popularized by Maria, and I think this is going to be really helpful for discrete random variables, especially if we're using gradient-based inference algorithms. And then we're really eager to try to make this highly parallelized. Right, it's something like a JAX, like a VMAP, is what we have in mind, right? And it's really nice if we can make it GPU compatible. It is GPU compatible to including Turing, right? It's you can kind of use CUDA arrays, but if you really want the performance from GPUs, you need some special treatment, I suppose. And Hong also stressed this interoperability, and this is also one of the themes, I think, where there's many probabilistic programming languages these days, and it'd be nice if we can combine everything to a certain extent, or at least we can write model in one language and use it to do inference together. The final thing is we want to transfer the license, right? This is better for the community and just generally better. All right, that's my talk. Thanks.